Hello everyone, welcome back. In this video, we are going to see about properties of Fourier transform. So these are all the properties of Fourier transform. The first property is linearity property, followed by time shifting, frequency shifting or multiplication by a complex exponential, time scaling, time reversal, multiplication by a power of t or differentiation in frequency, differentiation in time and integration, convolution in the time domain, multiplication in the time domain, followed by Parseval's theorem and duality property. Let us see the properties one by one. First property is linearity property. So this property is written based on additivity and homogeneity property. So here you can see the forward and reverse Fourier transform equations. The second equation is called as the forward Fourier transform, which is given as x of j omega is equal to simply it is written as x of omega, which is equivalent to integral is varying from minus infinity to plus infinity x of t e power minus j omega t dt. This is otherwise called as analysis equation, followed by the inverse Fourier transform equation, which is written as x of t is equal to 1 by 2 pi. Integral is varying from minus infinity to plus infinity x of j omega. This is the Fourier transform value of x of t. So since we are taking inverse Fourier transform, we are considering inside the integration x of j omega into e power j omega t d omega. Here we are integrating this function with respect to omega. This is otherwise called as synthesis equation. And now we see about the linearity property, right? So actually x of j omega is nothing but the Fourier transform of x of t, whereas here y of j omega is nothing but the Fourier transform of y of t. Here we are adding the signals x of t and y of t. In addition, a and b both are constants. A is multiplied by x of t and b is multiplied by y of t. And then we are adding a x of t plus by of t. Now we are applying the Fourier transform to the added function here. If we simply apply Fourier transform to x of t, we will get ax of j omega. Followed by if we simply apply Fourier transform to by of t, we will get by of j omega. So here, if we apply Fourier transform to the added function, we will get some other function that must be equivalent to the addition of individual Fourier transform of x of t and y of t, ax of t and by of t. So this is the with respect to this property. And ax of j omega plus by of j omega is the Fourier transform of the added function ax of t plus by of t. So here it is written there. Then the property of linearity. For the property of linearity, the proof is given here. Fourier transform of ax of t plus by of t. Here simply replacing x of t with ax of t plus by of t. So according to the Fourier transform formula, we are replacing this function instead of x of t. So integral is varying from minus infinity to plus infinity ax of t plus by of t multiplied with e power minus j omega t dt. Now we can write uh, this equation as a separate two integral equations, right? So due to this plus component here, we are multiplying e power minus j omega t dt inside the bracket, and then we are separating this integration as two integrations. So here integral is varying from minus infinity to infinity ax of t e power minus j omega t dt. This plus is given here, plus integral is varying from minus infinity to plus infinity by of t e power minus j omega t dt. Now we can take constants outside the integration. So in the first term, a is taken out. So it is given as a into e power minus infinity, a into integral e power minus infinity to plus infinity x of t e power minus j omega t dt. Similarly, the second term is written here. So now you can see and you can compare these two functions within brackets, right? these two functions with the Fourier transform formula. So the first uh, is the Fourier transform of x of t. The second one is the Fourier transform of y of t. So simply it is replaced as a into x of j omega plus t into y of j omega. This is the Fourier transform of the added signals ax of t plus by of t. So from this property, what we are coming to say is, if we add two signals and apply Fourier transform, that Fourier transform value must be equivalent to the addition of individual Fourier transform values of the two signals, right? So this is the linearity property. Next, we will see about the time shifting property. According to this property, x of t minus t naught is given. We apply Fourier transform to x of t, we will get x of j omega. Whereas when we apply Fourier transform to the time shifted version of the function x of t, we will get x of j omega multiplied with e power minus j omega t naught. Here t naught is nothing but the time shifting value, right? X of t minus t naught is nothing but x of t is shifted towards right by t naught units. So that this t naught unit is represented here. And this is the Fourier transform formula, right? For Fourier transform of x of t minus t naught is nothing but integral is varying from minus infinity to plus infinity. Instead of x of t, here we are replacing it with x of t minus t naught e power minus j omega t dt. Next we go for substitution method. Here t minus t naught is replaced with lambda. So here lambda is equal to t minus t naught, which implies that t is simply lambda plus t naught. Then we can substitute this lambda and t values in the above equation. Now we will get integral x of lambda e power minus j omega into lambda plus t naught into d lambda. Here we can split this exponential terms, right? Now if we split this exponential term e power minus j omega lambda into e power minus j omega t naught. So this e power minus j omega t naught is taken out from the integration. Now we can consider integral x of lambda e power minus j omega lambda into d lambda multiplied by e power minus j omega t naught. Here you can see, if we have x of t, the Fourier transform is written as integral x of t e power minus j omega t dt. Suppose instead of t, if we have lambda, t, lambda, these are all independent variables, right? So if we have lambda instead of t, x of lambda e power minus j omega lambda d lambda. So this is again the Fourier transform of x of lambda, which is expressed as x of j omega. So this entire integration term comparing to Fourier transform equation, it is written as x of j omega. And outside the integration, we have e power minus j omega t naught, which is a constant term, so which is multiplied with x of j omega. So the Fourier transform of the time shifted version of the signal x of t, which is x of t minus t naught, is equivalent to x of j omega multiplied by e power minus j omega t naught. T naught is any constant value, right? If suppose if we have a t naught is equal to 5 means a Fourier transform of x of t minus 5, right? So the Fourier transform of x of t minus 5 is equivalent to x of j omega into e power minus j omega 5. So suppose if we have x of t is equal to del of t. We know already what is the Fourier transform of del of t. For del of t, Fourier transform is equivalent to 1, right? Suppose if it is given as the Fourier transform of del of t is equal to 1, find the Fourier transform of del of t minus 5. You are asked to find the Fourier transform of del of t minus 5 means, so previous x of j omega is equal to 1 here. Now you have to multiply 1 with e power minus j omega 5. So this is the Fourier transform of del of t minus 5. So note that this means the time delay is equivalent to a linear phase shift in the frequency domain. The phase shift is proportional to frequency. Yes, of course. So we refer to a system as an all pass filter. If phase shift is an important concept in the development of surround sound. So modulus of x of j omega is equal to 1. The magnitude is equal to 1 here. And the angle of x of j omega is not equal to 0 since we have the exponential term e power minus j omega t naught. Thank you.